All right, so we went over some basics of substitution and elimination on Wednesday. So we're just gonna continue with that. And what I want to do before we jump into like solving problems and determining which mechanisms are at play is just kind of run through some generic substitution examples and then kind of go from there. So we're going to go through this really quickly on this first page. This handout is in Blackboard. It's in the, actually, you know what? I can go ahead and upload it to the chat. But it's actually in the assignments folder in the SN, I think it says substitution and elimination. That's the name of the folder. Let's see. But I have it here. Document. Must not have downloaded. Let me grab it right quick because I can put it in the chat. You can actually just get it now. Give me 1 second. Download this and then I'll upload it into the chat. Now. So I'm putting the handout in the chat. You can download it and follow along, but you can also find it in Blackboard. All right, so let's go ahead and jump right in with this substitution and elimination. And a lot of it is, some of it is going to be redundant because we've already talked about it. And today is the 17th. Right, so we've talked about Sn2, Sn1. We haven't talked a lot about elimination, but we've talked about these indirectly in several examples. We talked about it when we were doing alcohols to alkyl halides. We talked about it when we were doing, there was another reaction that we were looking at where we talked about it, whether it was Sn2 or Sn1. But so Sn2 is, I have that depicted here. And there's some things that we know right away that are going to favor the Sn2. And that is that it's going to be done on a primary or secondary substrate. What that means is that the carbon where your leaving group is going to be either primary or secondary, right? It does not work on on tertiary. And we talked about that before because of the approach of the nucleophile. Right, so tertiary doesn't work with that. And then one thing that we haven't talked about is the solvent. So it's going to be done in an aprotic solvent. And I think I sent one of the videos I sent you had a list of solvents in it, and there's actually a list in this handout. Let me see if I can scroll to it. Yeah, right here. So there's a list of different solvents in this handout. Right, so you got polar aprotic and then polar protic. So acetone, ethyl acetate, acetonitrile, DMF, dichloromethane, THF, all of these are what we call aprotic solvents, meaning they cannot donate H+. Right, so no protons to donate. And then protic solvents obviously are the opposite. They can donate H+. And that's an example of that would be acetic acid, really any type of acid. Alcohols, water, all of those would be considered protic. All right, so let's go back to here. We'll talk about the solvent and why aprotic solvents are necessary using this first example. So let me cut that out because we could just talk about everything with this example right here. All right, so let's take this example. First, let's predict the product. So this is a Sn2 substitution. Right, the S is for substitution, N is for nucleophilic, and the 2 is for what we call bimolecular. So it's that we're going to talk about the rate law and all that stuff in a minute. So it's a bimolecular reaction, meaning that it's going to have a 2-term rate law. And again, the S is for substitution and N is for nucleophilic. So let's see if we can predict the product. So this is one of the keys to going through these substitution mechanisms and determining what the outcome is to identify your nucleophile, which in this case is going to be this methyl sulfide moiety, and then this is my electrophile or my substrate. This is my leaving group, right? My leaving group, the leaving group is kind of easy to identify. Is normally like the most electronegative atom in the substrate. So bromine is an excellent leaving group. We're going to talk about all of this with this one example. So leaving group ability, solvent effects, and obviously the arrows and the mechanism and whether it's concerted, rate law and all that stuff. So we're going to cover all that. All right, so we're going to talk about leaving group, solvent, rate, and mechanism. All right, so what can somebody tell me? Let's start with the mechanism. Is this substitution type mechanism, Sn2 type, is it concerted or is it stepwise?
Concerted.
It's concerted.
Concerted. All right, it's a concerted mechanism. What that means is it points to the fact that it is bimolecular. All right, and that points to the rate. It's bimolecular. So the rate determining step will involve the nucleophile and the substrate. Right? So the rate determining step where the nucleophile is coming in and the leaving group is leaving, which we've already talked about, is going to involve both the nucleophile as well as the substrate. What that means for the rate law is that the rate is going to be K times the concentration of the substrate times the concentration of the nucleophile. So all those things tie together. The fact that it's bimolecular, that it's concerted, that the nucleophile and the substrate are both involved in the rate determining step. That means that the rate law is going to be a second order rate law. Right, second order overall. And so whatever I do to the substrate or the nucleophile is going to affect the rate. If I change the concentration of the substrate, that's going to affect the rate. If I change the concentration of the nucleophile, that's going to affect the rate. All right. So that's one factor to consider when you're thinking about the Sn2 type mechanism. Now let's go back up top and let's see if we can predict the product. So since this is a substitution, the nucleophile is going to substitute for the leaving group, right? It's that simple. Whatever your nucleophile is going to replace your leaving group. Now, how that happens is depending on some other factors like the solvent and things like that. But the brass tacks of it is that the nucleophile is going to attack the carbon where the leaving group is. The reason, very simple. You learned this in part 1. That's a polarized. You always look for a polarized bond, right? So that's a polarized bond where that carbon is partially positive, bromine is partially negative, right? So that partially positive carbon is going to be the site where your nucleophile attacks. So this is coming here like this, boom. And it's a double-sided, not double-sided, double-headed arrow. And then I'm going to lose my leaving group. All right. So what do I have on the other side of the arrow?
The SCH3 is attached where the bromine was.
Right, so that and this. Is that right?
Yes.
Right. Right, and that's it. That's the essence of substitution. So whatever your nucleophile is, even if you don't know how to push the arrows, you should be able to predict the products. Whatever your nucleophile is going to replace your leaving group. Now, the Sn2 is facilitated by good leaving groups. Right, so good leaving groups increase the rate. The question is, how do we determine what a good leaving group is? It's actually fairly simple, right? You can determine the leaving group ability by looking at the pKa of the conjugate acid. Sorry about that. There's a little bit of a lag in my Wi-Fi. All right, so you can determine how good a leaving group is based on the pKa of the conjugate acid. The lower the pKa, the better the leaving group. The higher the pKa, the worse the leaving group. So let's look at, there's also in this package, there's a list of acidity, pKa's, right? So you can see right here, bromine is an excellent leaving group. Let me thin that out some. Bromine is an excellent leaving group, right? You can see at the conjugate acid of bromine, which would be HBr, right? Has a pK of -9. That's excellent. That's highly acidic. And so how many of you remember from part 1 when we studied acids and bases, like what is that pKa loosely based on? Anybody remember?
Are you talking about like dissociation and stuff?
Yes, but we talked about, like, there were some factors that we talked about that determine pKa, right? Like hybridization, induction. Remember I gave y'all a acronym to remember it. HIRES, hybridization, induction, resonance, electronegativity, and size. Right, so what this number right here is saying is that this bromine right is stable if it has a negative charge on it. The lower that pKa is, the more stable the conjugate base is, which bromine is. If you're looking at HBr, then the conjugate base would be Br minus, right? So the lower that pKa is, the more stable that bromine is with that charge. In this case, the stability probably comes from the size of bromine. It has a large atomic radius, so that means that the charge is going to be more dispersed or more diffuse over the surface area of the atom. So, but yeah, so that's how we determine leaving groups. And the reason we're talking about this is because if we're comparing two substitution reactions and we're asked about the rate of one versus the other, then if we compare all of the factors and everything is the same except for the leaving group, then that's what's going to determine the rate. So the lower the pKa of the conjugate acid is on the leaving group, that reaction is going to happen faster because that leaving group is going to be more stable. All right. So let's go back up to here. Right. So the leaving group, we have a really good leaving group and bromine. And then our nucleophile, we're going to talk more about the quality of the nucleophile as well, because there's a way. I think I sent a video for that too. You probably may not have had a chance to watch it because I sent quite a few. But the quality of the nucleophile also matters, and that's based upon the solvent as well as the nucleophile itself, like where it's located on the periodic table. So we want to talk about that. I don't want to get into that right now because it makes more sense when you are comparing two reactions with a different nucleophile in the same substrate, rather than doing it now. But there's a trend for nucleophilicity based on the solvent, right? So if it's in a protic solvent, the trend is going to trend one way. If it's in an aprotic solvent, then the trend is going to be different. Going across, the trend stays the same, right? Nucleophilicity decreases from left to right in both protic and aprotic. But for the protic solvents, the trend from top to bottom in a group changes. So we're going to talk about that, but not right now. But what I do want to talk about with the solvent is whether or not it's protic or aprotic. Someone say here that. Did you have a question?
I thought we were talking about acetone being, I thought it was aprotic.
It is. Yeah, acetone is aprotic. But what I'm gonna say here is that protic solvents will slow the reaction down. Right, there's a reason for that. Right, so we know about the leaving group, better leaving groups based on the pK of the conjugate acid. We know about the rate law. It's a two-term rate law. So anything got changed with one term or the other is going to change the overall rate of the reaction. We know the mechanism is concerted. We'll put the arrows in last because we've already kind of seen that. But the solvent has to be aprotic, right? It cannot donate protons, and there's a reason for that, right? If my nucleophile if I have my nucleophile in a protic solvent, it's going to slow the reaction down due to a phenomenon or observation that we call solvation. Right? They're going to solvate the nucleophile. What that means, and as simplified a definition as I can give you, is that they just surround the nucleophile and decrease its reactivity. Right? So if I have that nucleophile here, and I put this in a protic solvent, those protons from that solvent are going to surround that nucleophile. Right, they're going to surround the nucleophile, and in turn, it'll decrease its reactivity. And that's for any Sn2 type reaction. And the reason why it matters is because, again, the nucleophile is a part of the rate law. So if I touch it, if I perturb it in any type of way, it's going to affect the rate. So if I'm using a protic solvent, then that nucleophile energy is going to, the nucleophile's energy is going to decrease. That's how the reactivity decreases. So let me put that in here. And I'm going to show you why that matters. Right? So it's going to decrease reactivity by lowering the energy of the nucleophile. It's going to make it more relaxed, and you know, as simplified a terms as possible that I can put that. It's going to make it more relaxed, less reactive, and what happens in terms of energetics, we can see here on an energy diagram. Right, so this is on the x-axis, we got time. Y-axis, energy. Right, so I'm going to put two curves. One of them is going to be in a protic solvent. So what I'm going to illustrate is that in a protic solvent, so here, this is your nucleophile in a protic solvent, right? So if I'm trying to get to this transition state in a protic solvent, if that energy of the nucleophile is less, then that's going to make the barrier or the activation energy higher, right? Decrease the energy of the nucleophile, then it's going to increase the activation energy. If I'm doing this in an aprotic solvent and the nucleophile energy is here, but the barrier is the same, right? You can see there. Right, that difference in energy is going to increase the rate of reaction, because now the activation energy is not going to be as high. Right, so if I do this in a protic solvent, it's going to lower the energy of my nucleophile, which in turn is going to increase the activation energy. So it's going to make the activation energy higher, slow the reaction down. All right. Any questions about that? So I don't want to do this in a product solvent. Bottom line, I want to do it in an a-product solvent where I don't have to worry about my nucleophile, my solvent competing with my my substrate for the nucleophile's attention, right? I don't have to worry about that. If I do this in an a-product solvent, then that's not going to be a problem. Right, so what do we know about the Sn2? We know that good leaving groups speed it up. We know it's done in an a-product solvent. We know that it's done on primary and secondary substrates. We know the rate law. It's a two-term law overall. And we also know the mechanism, right? It's concerted. We already put the arrows in, and we know that it all happens at the same time. So on the second page of this handout right here is basically an overview of the Sn2, right? Because there are basically two substitution paradigms, right? One is simultaneous attack of the nucleophile and loss of leaving group. And the other is leaving group leaving first, which is Sn1, which we're going to talk about in a minute. So the Sn1 type mechanism is different from the Sn2, and that is stepwise. So if you look here at the energy diagram, you can see the nucleophile and the substrate are here, right? And as they collide and begin to interact with one another, that's when you get to the transition state. And then you end up with your product, where now the nucleophile has replaced the leaving group. So it's concerted. The transition state involves both nucleophile and electrophile. And then this is, we talked about this before, but I'll show you this too, that the transition state itself has an overall negative charge, because the incoming nucleophile is going to be partially negative, and the outgoing leaving group is going to be partially negative. So the overall charge on the transition state is negative, right? That's important. And you can see the approach of the nucleophile. We talked about this before, and I'll just kind of reiterate it. The nucleophile is always going to approach from the opposite side of where your leaving group is, right? This is the reason why you see inversion, right? Nucleophile always approaches from the opposite side of the leaving group. That's why you always see inversion of stereochemistry. If your leaving group is on a chiral symbol. All right, questions about anything so far? All right. So what I want to do with this handout, since I've already done the first one, right? You'll do the second. You can finish that. We've done substitution already, so it's just a matter of drawing the product. I'm not asking you about all the other factors. I just need you to put the product in. So we've already done this one. All right. So this is so you'll finish the second. All right. So we talked about basically every factor with the Sn2. And the reason I'm doing it like this is because I'm laying the foundation. So when we start looking at trying to solve problems that ask questions about the mechanism, we can use this information to solve those problems, all right? So let's look at the SN1. All right, and it's gonna be the same thing here. We're gonna go through this first example. Put that on a separate page. And if you took my class for part 1, then I'm sure you remember this handout because we used the same handout. We just didn't go into as much detail. So for SN1, again, S is for substitution, N is for nucleophilic, and then the 1 is for unimolecular. Right? If the SN2 was bimolecular, what that means is that both the nucleophile and substrate are involved in the transition state. This is unimolecular. What that means is that, and when I say transition state, I mean of the rate determinant step. Right, when I say unimolecular, what I mean is that only the substrate is involved in the rate determinant step, right? Not the nucleophile. So this particular rate law is not going to be dependent on the concentration of the nucleophile. So let's do the same thing we did up here. Let's talk about the leaving group, the rate, solvent, and the mechanism. Right, so the mechanism is stepwise. And the first step in the mechanism, we're actually going to draw that out down here. So let me just, the first step in the mechanism is the loss of your leaving group. So we have bromine again as our leaving group. And this is spontaneous. It does not require any type of catalyst or anything like that. First step is loss of leaving group. And then we make a carbocation intermediate. Right, so that's the every SN1 mechanism is going to go through an intermediate, a carbocation intermediate. That's why the preference is to use a secondary or tertiary carbon. There are other types of substrates that work there too. You can use an allylic substrate. So something like this, where my leaving group is not there. Where my leaving group is here, because the intermediate will be stabilized by resonance. Everything comes down to stability. Right? You can use also a benzylic substrate. Where my leaving group is on a carbon that's attached to an aromatic ring. So we call this a benzylic substrate. Right, but those substrates also work for SN1 because making the carbocation is the rate determinant step. So you need that carbocation to be as stable as possible. Right, so the loss of leaving group this is the rate determinant step, right? And then your nucleophile comes in which in this case is OCH3, so methoxy anion. That's going to come in and attack right there at the carbocation. So you can see both Sn1, Sn2, they're both substitutions. So the core concept is to replace the leaving group with the nucleophile. But the difference is in how it happens. One of them is concerted, one is stepwise, one goes through a carbocation, one doesn't. So with the Sn1, we know that the leaving group, we need it to be a good leaving group. We know about how to determine if something is a good leaving group. So good leaving groups, it's the same as above. So good leaving groups are going to be good for any substitution or elimination. Right, so a good leaving group is going to increase the rate. The rate, since it's unimolecular and is not dependent on the nucleophile, because the rate determining step is the loss of leaving group. Right, it's a first order rate law, and it's just K times the concentration of the substrate. Nucleophile does not play a role in determining the rate. Right, so it's unimolecular, it's a first order rate law. And for the solvent, protic solvents, facilitate the reaction. And there's a reason for that. Let's think about it. Right, it's really the same principle of solvation, but now it's serving a different purpose. Right, so again, if we think about if this is my substrate, let's just think about the transition state. Where we have a partially broken bond to whatever my leaving group is. Right, and this is partially negative, and this carbon down here is partially positive. And this is the transition state for the rate determining step. Right, so imagine if you're doing this in a protic solvent, those protons are actually helping, because as the leaving group is leaving, let me fix these H's. Right, those protons are actually helping, because if this is the transition state and I end up with this intermediate carbocation and a negatively charged leaving group, those protons can solvate that leaving group and stabilize it.
I was gonna ask, what about, I guess, the reaction would make it like when the bromine or bromide does detach, like that the OCH3 is able to like go in faster than it would come back. So it's because of those protons.
Yeah, and that plus when you compare the nucleophilicity of oxygen to bromine, oxygen is a better nucleophile. So even if bromine is coming back trying to attack the carbocation, oxygen is attacking faster. That's a great question. But let me finish this statement and then I'll go back to that. Right, so a product solvent in this case is going to solvate and stabilize your leaving group. Right, so in the transition state, as the leaving group is leaving, it's pulling a pair of electrons with it. So it's got a partially negative charge, eventually a fully negative charge. And so that that product solvent is going to help to facilitate that process by solvating and stabilizing that leaving group. That's not to say that the product solvent won't solvate the nucleophile too, because it probably does, but the nucleophile attacking is not the rate determinant step. So it doesn't matter. The rate determinant step is the loss of leaving group. But back to your question about which one is going to attack faster, the oxygen is a better nucleophile. The trend for nucleophilicity and product solvents is that is decreasing from left to right across the periodic table. So since oxygen is across from bromine and but bromine is under oxygen, so it increases from top to bottom in a product solvent. But because bromine is to the left of oxygen, oxygen is a much better nucleophile, so it's going to attack that carbocation much faster. Yeah, there's not really a lot of competition between the oxygen as the nucleophile versus bromine in this particular case. That's a great question. Very thoughtful question. All right, we got to stop here. I'm 2 minutes over. I apologize about the link, but I'll get that squared away and send you a recurring link when I post the recording and post the notes and all that stuff. I got to go back into my Zoom account and make a